Hello, welcome to your physics teacher. In today's lesson, we're going to be looking at section 3.3 from the Nelson textbook, the section from Newton's second law of motion. And in this, I've chosen a couple of questions which are going to be useful for you. So please feel free to select the question that was challenging from the chapter menu on the browser below. But let's start from the beginning. So from question number 2, let's read it together. They want us to calculate the acceleration in each situation. Part A, a cannon exerts a force of 2.4 newtons, 2.4 times 10 to the power 4 newtons east on a 5 kilogram shell. Alright, so in this section, we know we're dealing with Newton's second law. So let's first write down our new formula. The net force acting on an object equals to the mass of that object times its acceleration. And since they are asking us to find the acceleration, what we can easily do, just rearrange this equation for acceleration. So we can divide both sides of the equation by the mass. And this will simplify to that the acceleration of the object equals to the net force acting on it divided by the mass. So this is going to be the new formula for solving this question. So now we can easily take care of part A. Part A, the acceleration is going to be the net force, which is 2.4 times 10 to the power 4 newtons in the east direction. And the mass of this cannon, not the cannon, but the shell from the cannon, is a 5 kilogram shell. So let's do this calculation now. So this, you get approximately 4,800 meters per second square. And we have to indicate the direction, which is going to be east. That was pretty straightforward. Part B is they're still asking us to calculate the acceleration, but we have a slightly different scenario. Let's just write down our formula. So we have acceleration equals to the net force acting on that object divided by the object's mass. And the question reads, there's a hockey stick and it hits a 160 gram puck forward with a force of 24 newtons. The trick that they're trying to do on you is that they're giving you the mass in grams. Make sure that you convert the units into SI units. So in this case, the SI units for mass is going to be kilograms. So in this case, the net force is 24 newtons divided by, to go from grams to kilograms, divide by 1,000, so 0.160 kilograms. And they don't give you the direction, so you can assume that it's moving in whatever forward direction we take it. So we can put the direction for acceleration as forward. Plugging this into our calculator, we get 150 meters per second square in the forward direction. The next question that we're going to do is question number 3. And question number 3, they want us to determine the mass of the object in each situation. The first situation is a driver brakes and the car accelerates at 1.2 meters per second square backwards, and the net force on the car is 1,400 newtons backwards as well. Let's start off with the first main equation of Newton's second law. The net force acting on an object equals to the mass times its acceleration. So if they're asking us to find the mass, we can divide both sides of the equation by acceleration. So the mass of the object is the net force divided by the acceleration. But there's a bit of a problem here. We have a vector divided by a vector, and this is actually not allowed. But there's something really interesting about the net force and the acceleration vector. because the mass of an object is always positive. So let's show you what I mean here. In this case, the mass of the object is always greater than 0, which means that the net force always points in the same direction as the acceleration of the object. If this is true, then that means that, if you recall the question, it kept on saying backwards and then backwards. So whenever we put into our calculations, the direction will cancel out. So if it was backwards, we put negative, backwards negative, negative divided by a negative will just cancel out. So we can instead write the net force divided by the magnitude of acceleration. This way we'll get something that's mathematically allowed, because dividing by vectors is not a mathematical tool that we're allowed to use. So whenever we want to calculate the mass of the object, just take the net force and divide by the acceleration. Now going back to the actual question, again, they were asking us to determine the mass in each situation. And now we have a formula. So the mass equals to the magnitude of the net force divided by the magnitude of acceleration. So here all we have to do is just simply take in the values that they're giving us. All right, we can approximate it to be 1,200 kilograms. Part B, they was also asking us to calculate the mass, so we can take the same rearranged version of the net force formula equation. And this case it's putting in the numbers, but notice once again that the net force is forward and the acceleration is forward, so in the same direction, so we can just take the magnitudes in this case. So we have the question. Oh, I got too ahead of myself. The question read, a woman throws a shot put with a net force of 33 newtons forward with an acceleration of 6 meters per second squared forward. So the net force will be 33 newtons and the acceleration is 6. So we roughly get the mass to be 5.5 kilograms. This next question, now things are getting much more challenging. It's not as easy as just plugging things into the formula. So we're going to have to recall what we've done before in the previous lessons. We have for question number 4, a 54 kilogram skier starts from rest at the top of a snow-covered hill, reaching a velocity of 12 meters per second in 5 seconds. Calculate the net force acting on the skier. Now, a good thing to do would be to consider the system diagram, then the free body diagram. In some cases, you can merge those two together. So that's what I'm going to do. I'm going to draw some snow-covered hill. So that's why it's in white. And when I used to snowboard, I had a red snowboard, so I'm going to draw myself. And here I am snowboarding. Alright. Notice that in this case we are on a slanted hill. This means that as the person goes down the hill, this could be our displacement. We can associate this displacement, instead of saying it's down some degrees east, we can just indicate the direction of the displacement by saying downhill. This makes things a lot easier, because now if we go back and read the question, it said that a 54 kilogram skier starts from rest. Once we have our displacement, we could take care of our velocity vectors. So initially, if you're starting from rest, it means you have 0 meters per second initially. And after 5 seconds, you reach a final velocity of 12 meters per second. And this all took place during the time interval of 5 seconds. And in this case, remember when we're doing projectile and kinematics, so we went from displacement to velocity, and we should have acceleration. The direction of acceleration will also be downhill, but this value you don't actually have, so it's going to be an unknown. What you do have as well is the mass of the skier, which was 54 kilograms, so we could have the m value, which is going to be 54 kilograms. Great. So now we have a lot of information, and in order to set up a convention, we're going to assume that whenever you're going downhill, that's the positive direction, and if the person wants to jump upwards from the hill's perspective, that can also be a positive value. So we have to set up our positive directions. Now, at this point, you probably already forgot what the question was even asking you, right? So the question was asking you to calculate the net force acting on the skier. Our net force is the big unknown. But now we have a connection, because we know that the net force acting on an object is equal to the mass of that object times the acceleration of that object. Normally we've been just plugging into the formula, but we can't in this question because we only have the mass, which was 54 kilograms. But the acceleration was a big unknown, so we need to go back and try to solve for it. And the net force is mass times acceleration, but notice that in order to get acceleration, we need to go back to our first unit where we talked about kinematics. So that means that we're going to go back and use the big 5 kinematic equations of motion. So let's write those down just so we can use them. Now, although I did say there are big 5 kinematic equations of motion, I find that in problem solving, I only ever need to use 3, where the first one is always the main equation, there's the second main equation, and then the third main equation. So these are the only ones you really need. The other two, if you get really stuck, then you use them. But otherwise, just list these 3. I find that students usually make a mistake when they try to use the other 2 equations. So just stick to these 3 for now. Alright, so what was our goal? Our goal, we want to find the acceleration of that object. So in this case, all 3 equations have acceleration, and we don't have the displacement, so maybe the first equation is not the good choice, or the third equation. So right away we filtered it out into the second equation here, because we were given the time interval, initial velocity, and the final velocity. So let's rewrite it down and put in what we were given. Now, because we did choose a coordinate system where downhill is positive, this means that the final velocity is actually a positive number because it was going down. And our initial velocity was 0 because the object started from rest. And the time interval that this took place was 5 seconds. And putting in all these values, we get 12 equals to 5a. And here the acceleration was going down, so that's why we took it as a positive value. Now at this point, all we have to do is divide both sides of the equation by 5. And we get that the acceleration equals to 12 over 5. This is useful because now we have the acceleration. We can plug it back into Newton's second law formula, and we have the mass. We can plug that into the formula as well. So now we can solve for the net force, which we get approximately to be 130 newtons, and the direction is downhill. Okay, so here I'm putting the whole question so you could take a screenshot and go over the steps on your own. So we did have to use kinematics, and we did have to consider the directions, and in this case we considered downhill to be positive, which was really helpful in this case. For question 5, we have a dynamics cart is pulled from rest by a net force of 1.2 newtons forward. The cart moves 6.6 meters, reaching a velocity of 3.2 meters per second forward. Determine the mass of the cart. Our first strategy is going to be to first visualize this. So instead of dynamics cart, I'm just going to draw a regular car. Okay, so we have a cart and it's being pulled from rest by a net force of 1.2 newtons forward. In this case, we are going to assume the forward is to the right. So here we have a dynamics cart and it's being pulled forward from rest by a net force of 1.2 newtons. So the direction is going to be to the right, let's assume, and this is by a net force of 1.2 newtons, where we're going to indicate that forward is the positive direction, and the cart moves 6.6 meters, so that's going to be our displacement vector, and we're going to leave it as positive, indicating forward, which is to the right. Now, because it is being pulled from rest, that means that the car's initial velocity is going to be 0. And they also give us that the mass, oh no, that's what we're trying to find. So we want to find the mass. All right, that's our unknown. All right, what else do they give us? And after 6.6 meters, at that point, it reached a final velocity of 3.2 meters per second forward. So after traveling that distance, the final velocity is 3.2 meters per second forward, which we're taking to be positive in this case. And in order to speed up, your acceleration vector must be pointing to the right as well. Now, in this case, we don't have the acceleration, so that's another unknown. So notice whenever you're trying to solve problems, it's kind of like kinematics. You visualize it. Normally, choose your coordinate system, where we define to the right as positive. Then you draw displacement vector, velocity vector, then acceleration. But now, because we're in the second unit, we also have to consider Newton's second law. So let's write down the second law. The net force acting on the car equals to the mass of the car times the acceleration of the car. And because the question was asking us for the mass, notice that we can connect kinematics to forces through Newton's second law equation. So we can rearrange this to calculate the mass, which would be the net force divided by the acceleration. The net force, they gave it to us as 1.2 newtons, but the acceleration is what we're trying to find. So like I was mentioning, Newton's second law connects forces with kinematics because forces cause motion. So in order to solve some questions, we are going to go back and use the big 5 kinematic equations of motion. So let's write them down just as a quick recall. Okay, so although I did say the big 5, as I mentioned before, I only try to use 3 of them because this is all you're ever going to need to solve most of the questions. So looking at our diagram, we're trying to find acceleration. So all 3 of these are pretty good candidates. And the only thing that we don't have is the time interval. So we want to eliminate the equations that include a time interval, which is going to be 1 and 2. This means we're going to use the time independent equation, which is number 3. So let's rewrite it, and then we're going to put in the given values to isolate for the acceleration. And in this question, we had that the initial velocity was 0 because it starts from rest. The final velocity is positive, pointing to the right, so it's 3.2. Our acceleration is what we're trying to find, but the displacement is positive, pointing to the right, so we're going to replace it by 6.6. So let's simplify our equation now. (3.2 meters per second equals to 2 times 6.6 times the acceleration. Oh, but this was 3.2 square. I almost made a mistake. To simplify for the acceleration, we need to isolate for it, so divide by the coefficient of the acceleration, which is going to be divide both sides by 2 times 6.6. So finally, we're going to get that the acceleration equals to 3.2 squared divided by 2 times 6.6, which is approximately 0.78 meters per second square. And recall that to find the mass of the object, we already had the net force, and the only thing that we're missing was the acceleration, but now we found it, so we can substitute it into the equation. So it's going to be 1.2 newtons divided by 0.78 meters per second square, which will give us that the mass of the cart is approximately 1.5 kilograms. Okay, so here we have question number 6. During a parachute jump, a 58-kilogram person opens the parachute and the total drag force acting on the person is 722 newtons up. They want us to calculate the net force acting on the person and to also determine the acceleration of the person. So let's try to visualize this. So we have a parachute jump and a person opens their parachute and there's some drag force. So the person is falling down, and then the drag force will be pointing up because it's resisting the direction of motion. Let's draw a diagram so we can better visualize it. Okay, so we have the parachute and the person is falling, and as they're falling, there's going to be some drag force, and the drag force opposes the direction of motion, so the drag force will be pointing up. F drag 720 newtons. And the person has a mass and they're on Earth, so they're going to experience the force of gravity downward, which would be mg. Now in this case, the person is falling perfectly vertically downward, so there's no side to side. Not very realistic, but I guess for physics they try to simplify our lives, right? So along the vertical, these are the only two forces acting on it, and they're asking us to find the net force. So the net force is our unknown. But they actually give us the mass of the person, which was 58 kilograms. Okay, so in order to calculate the net force, we had to identify what are the forces acting on the person. Well, in this case, there are only two forces. And remember, the net force is the sum of all the forces acting on the person. So the net force is just the sum of all the forces, which is the drag force, plus the force of gravity. And then we're only interested in the y component of it. So the net force, we don't know the direction, so I'm leaving it as a vector. The drag force is 720 because it points up, I took it as positive. And the force of gravity, it points down, so we put negative mg. Substituting in our values, 720 minus 58 times 9.8. Calculating this, we get approximately that the net force equals to 151.6 newtons upwards. So from our diagram, that sort of makes sense, right? Because the drag force is making the person slow down as they're falling. Otherwise, you'll be accelerating to your death, and that's not very good, right? So here we have the net force points up, which makes sense because you should be slowing down with the parachute open until hopefully reaching terminal velocity and then making a nice land on the ground. But the question is not finished because they were asking us to find the acceleration. So from the net force, then we can use Newton's second law, where the net force acting on the object equals to the mass of the object times its acceleration. We can isolate for the acceleration by dividing both sides by the mass. (151.6 newtons up), and the mass was 58 kilograms. We get approximately 2.6 meters per second up as the acceleration. That makes sense. That makes sense. Question 7. A net force of magnitude 36 newtons gives an object of mass m1 an acceleration of 6 meters per second square. The same net force gives m1 and another object of mass m2 fastened together an acceleration of 2 meters per second square. What acceleration will m2 experience if the same net force acts on it alone? This question here is a bit of a puzzle. There are three scenarios happening at once, and the best way to tackle these type of questions is to draw a scenario for each one separately. So in the first scenario, we have the net force acting on m1. Second scenario, we have the same net force acting on mass 1 and m2 when they're fastened together, in other words, attached. And the third scenario, they want us to calculate the acceleration, once again for the same net force, but this time only acting on mass m2. So let's draw a situation so we get a better idea of what's going on in this question. So as I mentioned, here we have three cases, and each of the three cases we have the same net force acting on it. And the first one, the net force acts on mass 1, which gives us some acceleration. In the second case, you have the same net force acting on the mass 1, mass 2 attached. The third case, the same net force, but now only acting on mass 2. In order to answer this question, they want us to find the acceleration of the object of mass 2 when it is alone. But to do that, we're going to start from case 1 and get the mass 1 from Newton's second law. And then from the second case, we're going to isolate for mass 2. And then finally, in the third case, we're going to just find the acceleration for the object m2. So the mass 1 is going to be the net force acting on it divided by the acceleration. So 36 over 6 is going to be 6 kilograms. So that was from Newton's second law, right? Mass equals to the Fnet divided by the acceleration. And likewise, but now for the second case, we have mass 1 and mass 2 combined. The same net force of 36 newtons, and in this case the acceleration is 2. So mass 1 plus m2 is going to be 18 kilograms. Isolating for mass 2 on its own is going to be 18 kilograms minus mass 1. This means that the second mass is going to be 18 minus 6, which will give us 12 kilograms. This is going to be useful because now for the third case we can just use the mass that we just found into the Newton's second law formula to find the acceleration. So as we saw before, acceleration is the net force divided by the mass. And since we're only talking about the object mass 2, it's going to be 36 over 12, which we get the acceleration to be 3 meters per second square as a magnitude, but direction we could assume to the right in this case, or forward you can put. So in this, the strategy is we broke it down into different cases. That way it allows us to do this step by step, and that becomes a bit of a puzzle, which is how you should be approaching questions later on. Question number 8, we have a 1300 kilogram car. It accelerates at 1.6 meters per second square east. There's a frictional force of 3800 newtons west acting on the car. They want us to draw a free body diagram of the car and to determine the applied force acting on the car. Now in this case, although they don't ask us, a good way to answer this question will be to first draw a system diagram. So let's draw a car. And what we are given from this is the mass of the car. It's 1,300 kilograms. And the acceleration that they gave us is 1.6 meters per second square towards the east. We're going to take the east direction to be positive, so that way we could just write the acceleration vector is just 1.6 meters per second square. And they also tell us that there's a frictional force of 3,800 newtons west. F, and we're going to take west to be negative, so we could write negative 3,800 newtons. This means that there must be some applied force which is going to the right, which should be greater than the frictional force in order for the acceleration to be to the right. And we're going to find this value. So this is the applied force, F applied. So the applied force is going to be pointing to the right. Now in this case, normally we will have, we'll draw the normal force, which points up, and the force of gravity pointing down. But because the cars are not moving upwards or downwards, we're assuming that these two forces are being balanced. So vertically, they're equal to one another in magnitude, but in opposite direction. So this is going to be helpful because when we're looking at the net force, we're going to be interested only along the horizontal component. So let's write Newton's second law equation. The net force equals to mass times acceleration. And looking at the x components only, we have that the applied force points to the right, so it's positive. Frictional force is negative because it's to the left. Mass times acceleration. But the acceleration we can also simplify further because it was pointing to the right, so we took it to be a positive number as 1.6. So putting in the values for the frictional force, it was 3,800 newtons. So notice here, I put the magnitude was just the 3,800 newtons part, and the negative was indicating the direction. So then we can isolate for the applied force to be mass times 1.6 plus 3,800 newtons. And the mass of the car was given to us as well, 1,300 kilograms. So plugging this into our calculator, we get approximately 5,880 newtons as the magnitude. And if we want to indicate direction, we will put with a vector sign and then put east, which makes sense because the acceleration was to the right. So our net force should also be to the right because net force and acceleration are always pointing in the same direction. Our next question, number 10, we have 3 students push horizontally on a large 80 kilogram crate sitting on the floor. 2 of them push to the left on the crate, each with a force of 170 newtons. The third pushes to the right on the crate with a force of 150 newtons. And they want us to assume that no friction acts on the crate. They're asking us what is the acceleration of the crate and what will happen to the net force and acceleration if a 4th student jumps on top of the crate. And they want us to explain our reasoning. Wow, this is a very long question. It's quite complicated too when drawing the diagram as well. Now, I'm going to show you a new trick here. When you're solving Newton's questions, like force type questions, you could draw it looking at a side view, or what I like to call the bird's eye view. And in this case, because they're assuming that the crate is not moving up and down or on an incline, if we were to just think about the components along the y, which would be the gravity and the normal force, they would balance one another out. So let's just try to show that so it's easier to visualize. So here we have 2 students pushing to the left and 1 student pushing to the right. And we can assume that because they're on a horizontal surface and they're not applying a force at an angle, that the force normal is balanced by the gravitational force. So those will be balanced. So a better way to try to visualize this is to approach this question from a bird's eye view. Now from this bird's eye view, we can see much clearer 2 students on the right and 1 student on the left, and it helps us to see this so that we can see the direction of the forces. So we have the students pushing to the left and 1 student pushing to the right. So that's the bird's eye view, because if you saw the diagram on the left, it was hard to tell that there were 2 students acting on it, so it got too complicated. So this is the bird's eye view. Now the free body diagram is going to have 1 force to the left from 1 student and then the other force to the left from the other student, and then a third force to the right from the third student. Okay, so it's a bit complicated. That's because this question is so long, so I'm going to try to go a bit slow now. Once again, let's go back and read the question. So we have that the mass of this crate is 80 kilograms. And they're pushing on a horizontal floor, which is why I was trying to tell you that the normal force is balanced by the force of gravity. And the two of them that are pushing to the left, they each have a force magnitude of 170 newtons. And the one pushing to the right has a magnitude of 150 newtons. Okay, so this is much clearer, I think. And now, what are they asking us to find? What is the acceleration of the crate? So we're going to use Newton's second law. So they want us to find the acceleration, but in order to find the acceleration, we use Newton's second law. So the net force acting on the crate is the mass times the acceleration. And we're only interested in the forces acting horizontally. So we don't have the direction of the net force, but we know that it's going to be the sum of all the forces acting on the crate which would be mass times acceleration. So what are the forces acting on this crate? Horizontally, F1 is to the left, so it's negative. F2 is to the left, so it's negative. F3 is positive because it's to the right. And the acceleration, we're going to leave it as a vector quantity because we don't know if it's to the left or to the right. Putting in our values, we get approximately negative 190 newtons equals to the mass times acceleration. And in order to isolate for the acceleration, we're going to divide both sides by the mass. So negative 190, and recall that the mass of the crate was 80 kilograms. So our acceleration vector is going to be 2.375 meters per second square. And because it's negative, we can associate that with being to the left. Which makes sense because here we had 170, 170 both to the left, which is much greater than just a single 150 to the right. So our acceleration vector should be in the same direction as the net force, which was to the left.